Thank you very much, and good afternoon, everyone. Today I would like to present my research about wind and Doppler compensation for spread spectrum sound-based positioning system. Positioning system has an important role in agriculture, especially in the practice of precision farming and robotics. For example, for soil and yield mapping, plant monitoring, and also for navigation of an autonomous vehicle. And there are various kinds of positioning system, and among of them, global positioning system or GPS is the most widely used and adopted. It can provide very high accuracy, but it also has some limitation. It is relatively expensive, and also in certain conditions it cannot be used, for example for indoor and for hilly or mountainous area due to the absence of the signal. So that's why there is a demand to find an alternative positioning system, and many research has been done to address this issue. So considering several alternatives, we consider that sound is a good choice for developing alternative positioning system because it can provide high accuracy, and we can also develop the system using the component of audio system which are readily available in the market and inexpensive. And also it is also good to deal with the obstacle, especially when we use low frequency wave. And more specific, in this work, we are interested to use spread spectrum sound. So this is the figure illustrate the generation of spread spectrum sound from sine wave and M sequence code. So this is the typical spread spectrum sound signal. So it has special characteristic. It has high noise tolerance and also high signal identification properties that make it suitable for our application in agriculture area. And actually, the system has been used in the previous work. For example, in the Whisper and 3D Locus project, we can find this project. But the problem is, this setting is totally different with the environmental condition. Because in agricultural environment, there are many challenging factors we have to handle. We have to deal with high uncertainty, for example, temperature gradient, wind, humidity, and also for some mobile application we have to deal with the Doppler effect. So this is the overview of the system that we want to try to develop. Basically, we want to develop a low-cost positioning system with high accuracy. That means it should be able to handle and minimize many influencing factors like temperature, wind, and so on. And it is also important to make the system to be easy to deploy and also has high scalability. Of course, there are a lot of work have to be done and also maybe take a long time. And for the current research, we just focus on this issue, the development of wind and Doppler compensation, and we'll little bit discuss about the issue about the easy deployment and to address the scaling up issue by proposing self-calibration method. So next, I will discuss a little bit about the basic of spread spectrum sound positioning system. So this is the basic configuration, and also this is the device we use. We use a microphone here and omnidirectional speaker. So to develop such kind of positioning system, first we need to set several reference at known position, and then to estimate position of an object, we need to measure the distance from the object to each reference point. So we have several distance data, and then using this information, by using trilateration, we can determine the object position in 3D space. So this is the basic, and we can understand from here that the accuracy of the positioning system is strongly related to the accuracy of the distance measurement. So distance measurement is very important. So this is the basic distance measurement by using SS sound. So first, the sound will be transmitted from the speaker to the microphone. In the same time, with the emission of the signal, we also send the trigger signal to record the output time here. And once the sound reaches the microphone, we can recognize the input time here, the arrival time. So from this information, the time of flight of this signal, we can determine the distance by multiplying with sound speed here. And to get more accurate sound speed measurement, we use this equation. So this actually is a Newton-Laplace equation. We can get more accurate sound speed estimation here. So this part describe more detail about how we can get the input time here. So basically we take the correlation from the received signal and the replica signal that we already known from this signal actually. So from this calculation, well, when these two signal will match, we can observe this correlation peak here, that this is correlated with the input time. So we can estimate the arrival time of the signal from this peak. So there are some properties that important related to the spread spectrum sound, and this is the properties we use in our work. And more specific, this is the important part is about the selection of the frequency of the carrier wave. I'm sorry, it's not so clear. So in this work, we select 24 kilohertz as the carrier wave. So to determine this frequency wave, actually we have to know the characteristic of sound wave. So basically, low frequency wave will give great distance. It can travel a long distance, and also this is good to deal with the obstacles. But in the other hand, the high frequency wave will give better accuracy. So it should be like a trade-off. So to determine the proper frequency. And another consideration is about the noise. So we also try to investigate the noise that generated by several agricultural machineries. And we found that typically the noise is in the range of low frequency. So that's why we want to avoid this noise. So we select 24 kilohertz as the frequency wave. So this is the first property that we determine, and we consider this selection is quite good for our application. So another consideration is about the configuration, because the configuration will also determine the performance of our positioning system. So at least there are two configurations we have here. So the first is GPS-like system, and the second is inverse GPS system. So for GPS-like system, it will be better to be used for large-scale system. But this is not good for mobile application due to the simultaneity. So we cannot get the distance measurement exactly in one point. So that's why this system is not good for the system that requires high mobility. And in the other hand, the inverse GPS, this is good for mobility, but if we use the system for high scale, it will be a problem with the communication issue, because for this we can know that from the transmitter we will send the signal and then receive by the microphone here, and then we need to send back this information to our mobile system here. So that means it will be a problem if this scale will be scaled up to more device. So this is another issue related to the configuration. So next I will discuss about the wind compensation method for spread spectrum sound by using a base station. So as I mentioned before, that for agriculture area we need to deal many factors, and for the outdoor application, the wind is one of most important factors. And from this equation actually, so it will be, let's say, the error we obtain from the outdoor application mainly due to the inaccurate estimation of the sound speed. So as we mentioned before, that actually we can estimate the speed by using this equation by including some temperature influence here, but this is not enough for the outdoor application. So we try to get a more accurate estimation of sound speed by using a base station that we set at known position, so we can get more accurate sound speed estimation. So in this work we try to evaluate two different setups. we set the base station inside the working area and also outside working area. And here we see that we use two speaker or two transmitter. That means we need to use a multiple access technique here. There are at least three methods you can use, like code division multiple access, frequency division multiple access, and time division multiple access. But here we select to use time division multiple access, and we update the position every 500 milliseconds. So the update rate using this system is about 2 Hz. And in this work, we just consider about 2-dimension case, because we consider that this is the area we work. The working area is about 30 by 30 meter, and the height of each node is about 1.5. So we consider that actually we just consider about 2-dimension, and we can it also give enough result for the 3D case. So for our calculation, actually for simplicity, we just consider about 2-dimension case. So the basic idea of this wind compensation is just use known sound speed velocity to estimate unknown speed velocity. So at first, we need to set the base station and also the reference at known position. So by measuring the distance and flight time of the sound from the base station to each node, we can calculate the sound speed at base station. And this information we can use to determine the sound speed at this unknown position. This is mobile station. So basically, we just use a simple interpolation method here. So the first assumption is we consider that the sound speed will change linearly within this area. So this is the first hypothesis. And the second one is wind compensation when we set base station outside the working area. So basically the same, but the problem is here. So from calculation, we will have about half of sound speed velocity here. So for other half, we need to take the inverse calculation. So we can calculate the inverse sound velocity. It means the sound velocity at the opposite direction. We can estimate by using inverse calculation. So this is our second hypothesis, that we can estimate the sound velocity at the opposite direction by using inverse calculation. And the remaining process is the same. We just use a simple interpolation method. So to evaluate the effectiveness of this method, we conducted experiment like this. We set experiment and we take two different base station setup. The first is outside the working area, this little bit outside here, and the second inside, and we set the second setup exactly in the center of the working area, and we take 9 measurement points and we evaluate the positioning accuracy by using these two different setups. So this is the result. So this is the condition. Unfortunately, we conducted this experiment with a relatively low wind condition, just below the 3.5 meters. So actually, we cannot really evaluate our system. Is it good or not for wide range wind speed? But we can confirm here that for the base station set inside the working area, it can give better performance. So it can reduce the error almost 1/3 of those without the compensation method. So from this result, we try to evaluate what our hypothesis, is it correct or not. So from the experiment, we saw that for base station located inside working area, it gives quite good performance. It indicates that our first hypothesis, that the sound speed can be estimated by using interpolation method, and the speed of the sound change linearly. This is quite acceptable. So it is correct. But from the second experiment, that base station located outside working area, we see that the performance is not really good. So we need to consider that this hypothesis, it seems like this is incorrect. So we cannot just estimate the direction of the speed in the opposite direction by using inverse calculation. So maybe the condition more complex, so that we cannot use just simple inverse calculation. So from this experiment, we can conclude that by using the proposed compensation method, we can greatly improve the positioning accuracy. So from the experiment, we can obtain that the error can be minimized up to 1/3 of those without wind compensation. And of course, in this experiment, we only evaluate in relatively low wind condition. So we need to further evaluation to see is our system also works well for high wind speed condition. And the main issue in this proposed method is about the updating rate, because we use TDMA, so the updating rate is relatively low, about 2 Hz, and it is not sufficient for common application. So we need to consider about this issue. And one possible, some possible improvement is maybe we can try to use CDMA, because it will make the updating rate become faster. But to use this system, we have to deal with the near-field resistance problem that is common for this kind of system. And another solution, maybe we can combine with other sensors to overcome this low rate, that maybe we can get the position in between the updating by using other sensor. So next, I will discuss about the moving object localization by using spread spectrum sound-based positioning system with Doppler shift compensation. So this is the Doppler effect, because we deal with the sound wave. When the object in motion, the object will experience Doppler effect that will make a frequency shift. And this frequency shift will generate a problem with the signal identification. So this is the illustration. So this is the received signal with Doppler shift. And then we take correlation with the replica signal. This is the original replica signal, because there is a small shift from the original frequency. Then the correlation, we will like this. There is some decrease of the correlation peak that makes the signal identification become difficult. So to overcome this problem, we propose the method. The first, we detect the Doppler shift that's experienced by the sound wave, and then we recreate new replica signal by using this information. And from this new replica signal, and then we can take the correlation, and then we can maintain, sorry, this is still another problem. It should be, we can maintain the correlation peak still high. So we can maintain the signal identification. So this is the process actually. We add, beside the spread spectrum sound, we add another sound signal to detect the Doppler shift. So we can see here we add 36 kHz sound signal here, and then we can use this to detect the Doppler shift. So basically we can observe, after calculating the correlation, we can see the Doppler shift. For example, this is the original peak, should be in 36 kHz, and due to the Doppler effect, it will be shifted, maybe higher or lower. So we use this information to recreate new replica signal and use it for cross correlation calculation. So to evaluate the effectiveness of this method, we conducted 2 experiments. The first, we want to evaluate the influence of moving object with the signal identification. So this is the result. You can see that this is for non-compensated, and this one for the compensated system. So we can see that by using the compensation method that we propose, we can keep the correlation peak still higher. So we can easily detect this peak, and therefore we can estimate the time of flight accurately. So the second experiment tried to evaluate the positioning estimation, the positioning performance by using proposed depressive compensation method. So we set mobile platform like this that can move in this circular path with a variable speed from 0 to 1.3 radian per second. So here we use the inverse GPS configuration because as I discussed before, it is good for systems that require high mobility. So this is the result. We can see that for all speed, the position of the moving object can be estimated accurately. And from our evaluation, we can see that we can keep this positioning accuracy within 3 centimeters. So it's quite good for this result. And actually, 1.3 radian per second is equal with 1.3 meter per second. Actually, it's not the actual limit because this is just the limit of our device. So of course, we need to confirm what is the actual limit of our system. So from the experimental result, we can confirm that the proposed compensation method can greatly improve the accuracy for moving object localization. And in this work, because the limitation of our device, we only evaluated with the speed of 1.3. Of course, with the performance that's quite good, about 3 centimeters, we can expect that the system also works well for higher speed. But of course, we need the further investigation to confirm it. And the last part, I will discuss about self-calibration method. This is our attempts to scale up the issue, because in the previous work, like the for wind compensation and moving object localization, we just working with a relatively small area. So to scale up the system to wider area, we have to consider about the self-calibration method. So why this is important? Because like we discussed before, the first step that need to set up our system is to set the reference point at known position. So we call this process as calibration. So basically we can perform this calibration process manually. Of course, this is not convenient because it takes time and laborious. So self-calibration is highly required. And our opinion is, we confirmed before that we can improve the accuracy by using wind compensation method by adding additional base station. So we want to try to combine these two issues about the self-calibration and wind compensation. So not only to self-calibrate the system, but also we want to use it to enable wind compensation. So this is the basic idea. So this is the setup that we propose. Instead of using 4 points, here we propose using 5. So this is the basic idea. We combine the self-calibration and wind compensation. So to perform this self-calibration, then we propose this setup. So for each point, we modify, not only using microphone or speaker, but we combine this speaker and microphone that enable 2-direction measurement. By using this 2-direction measurement, we can improve the distance measurement accuracy. And therefore, we can expect that from this accurate distance, we can also get the accurate self-calibration result. So this is the figure of our device. So this is the proposed method. Basically, we also try to solve all unknown position, that means the position of each point here, simultaneously. But unfortunately, we cannot do this very well because sometimes our calculation cannot give the good solution. So instead of using simultaneous approach, we use step-by-step approach here. So we just take small triangle here. From this shape, we can take just small triangle and by using some simplification, we can make the system. So here we set, for example, the point number 1 we set as 0.0 and h here is a predetermined height. By using this simplification, and then we can make this system become fully determined. So we have 3 distance theta and we only have 3 unknown variable here. So that's why for this full determined system we always get the solution for this. So we can solve this equation step by step, and finally we can solve all unknown variable for this calibration process. So we conducted experiment in the greenhouse like this, and actually we conducted the experiment with different condition. So here we set the windows, and also there is some fan. We can set the different condition, but due to limitation of time, I will not discuss more detail about this. And in general, I will show this result that for different cases, we can still get quite good self-calibration result. So we can set this 5-node position quite accurately within 5 centimeter error here. But for 3-dimension case, we can see that this is a quite big error here. But if we consider only 4 base station that we use for getting the position, or later on, after we finish this self-calibration, of course we use this reference to get the position of some object we want to localize. So if we only consider this 4 base station, we can see that we can also keep, for 3-dimension, we can also keep still within the 10 centimeter. But of course, this is quite big error. Then we try to evaluate what is the performance when we use this self-calibration result to determine the position of an object. So we compare the positioning accuracy using self-calibrated system and manually calibrated system, and we have this result. So for self-calibrated system, the error in 2 dimensions is about twice of the result we obtained by using manually calibrated system. So this is quite poor performance, but of course we can consider in some condition that not required very high accuracy, we can still use this system. So this is some concluding remark that from our experiment we can confirm that the proposed self-calibration method can be performed within average error about 5 centimeter in 2 dimension, and 10 centimeter in 3-dimension case if we only consider 4 reference point. But for the 5th, is still very poor. And even though in the system we saw that the performance by using self-calibrated system is much poor than manually calibrated system, we can still consider to use this system, especially for some application that not require very high accuracy. For example, in condition that relatively flat, where the Z information is not really important, we can use this system. So from the experimental result, we can confirm that what we propose here, the wind compensation and Doppler shift compensation, can greatly improve the performance of the positioning system. But the current system, I think, is very limited because this is still very early stage, and many works we have to done to make it a better performance. But we can see that even for 2-dimension case, we can get quite good accuracy in the few centimeter, and we can consider the system to be applied in the special condition where the Z information is relatively not so important. So of course, by looking at the overview of our system, this is very big picture, very, convenient system, but of course it's still long away to achieve this system, and a lot of work need to be done to realize what we propose. So there are some possible improvement that maybe we can conduct it in the future. especially to improve the current system. The first is about the updating rate. We have to consider about the use of CDMA system, but of course we have to deal with many problems because the CDMA system limitation is about the near fall resistance. We have to deal with this. Another important thing is in agriculture, there are a lot of obstacles. Of course, we have to try to deal with this issue. So mitigation and compensation for the obstacles that will create the multiple problem is also important issue. Another thing is about scaling up issue, because here we propose some self-calibration method, but the performance is still very poor. So we need to try to find another alternative that can give a better result. Another important, maybe interesting topic is about development of the application by using the developed system. As I mentioned before, even though there is some limitation because the accuracy only good for two-dimension case, but of course we still can use this system to develop several applications. And one important thing is because our target is to develop low-cost system, so actually we need to really analyze from the economic point of view in which scale actually the system can be applied and we can get the optimum benefit from our system. So that's all. Thank you very much.
In respect to your wind compensating system, you mentioned that in the current results, with relatively low wind velocity, you may obtain good result of the compensation by linear interpolation. So, what happens if the a relatively high, strong wind velocity happens? So, is that linear compensation method is still okay, or you have to move to the non-linear methods to compensate that wind?
So, thank you very much for the question. Actually, for this compensation method, basically, of course, we understand that in the field there is not non-homogeneous condition, and this approach actually we take the average. So, for example, here we measure the distance from this base station to its reference node, and here actually we take the average of the sound speed in this area. So, in my opinion, even for the higher speed, it should be applicable. But the problem is not about the wind speed itself, but also how much or how fast the wind will change. Because in our system we use TDMA, time division multiple access. It means the time become an important problem. If the wind changes rapidly, maybe it will be a problem and we cannot overcome this. So this is, I think, in our opinion, for the higher speed, but how to say, not in the rapid change, I think this system also still can perform quite well.
Anyone?
Could you slow slide 19, please?
Hi.
In that slide, you don't mention base station configuration. You, in your thing, you made a particular point of doing base station configuration outside and inside, and showing that the inside was the better one, but it doesn't seem to be mentioned in your conclusion.
Oh, hi. And actually, I mentioned in the first conclusion actually that using the proposed compensation method, this means I take the best condition. We're using a TDMA and base station at the center of the working area. So we mentioned about this. So this conclusion actually is from the best result we obtained. So maybe I need to add another one point about one conclusion about what is the configuration actually. So I think, but actually I also discussed a little bit in this first conclusion actually. So this is, or maybe I need to add more strong conclusion about this configuration. So what do you think, Sisi? So I need to add.
because it has many words and it's very hard to read all along there, I didn't pick up that the conclusion
there
recommends that the base station needs to be in the inside.
So I think I will rewrite this.
Okay.
Okay, thank you.
Then some highlight.
Hi.
Some, only those very important conclusion part.
Hi.
Anyone?
You have done compensation for wind, then you have done separately compensation for Doppler shift.
Hi.
Are there any potential when you go for a mobile outdoor station where there is both wind and Doppler shift and humidity, there are going to be interactions?
Yes, this is an interesting question actually. So for the Doppler shift compensation experiment, actually, we also evaluate the influence, not only the object speed, but also the influence of the wind and also the noise, but I did not mention here. So maybe I will add in the another slide during the discussion that actually we also confirm this. And we confirm that actually the wind and also the noise not significantly influence the Doppler shift compensation. And of course, actually, in the final goal, we want to try to combine this compensation method using the base station for wind compensation and Doppler shift compensation to compensate the object movement. But we haven't finished with this actually. So I think these are also interesting topics. We want to evaluate what actually happened in the real field.
Any other thing? When you use a base station, the position for the base station and the distance between that position, base station position and the robot position would be 20 meter or 30 meter. Those possibility, because your
Yes.
range, measurement range would be 30 meter, 40 meter.
Yes.
Such a situation in the field, open field, may be different wind velocity.
Yes, of course.
You saw some problem.
But this is a challenge actually, because in the field this very complex condition, so that we can try is just to try to minimize. So that system actually we confirm that it can minimize. But of course in the application maybe the more complex condition and maybe this is not enough to compensate this influencing factor. Maybe this is also the case, but we can prove here actually that we try to minimize this negative influence. So we try to keep this.
Yeah, minimize way maybe the moving average many times and checking the some confirmation where the robot is and should be robot is between this and the robot should be between those some mapping systems for actually another compensation.
Hi. So that's why also we discuss here not only to address this issue about the complexity, but also about the updating rate. So that's why we also suggested that we can combine with other sensors. For example, we can use the odometry. So we not depend only from our positioning system using SS sound, but also we have another sensor to get the better position as actually.
Another sensor is
yes, this will be another cost. Of course, this will be another issue, but that's we want to try. So, is it really actually how to say when we add another sensor will be still cheaper or more expensive? We don't know. Actually, this is cheaper or more expensive than GPS system. So that's why I mentioned before that we need to conduct some economic analysis to see clearly what is actually our system is really cheaper than GPS or not. Because this is just our opinion that we can develop the system using low cost audio system. So that's why we can expect that this system can be cheaper than GPS.
We may expect another question. How much would be if you with this system if we succeed?
From our research group, actually, we already developed the system in the small electronics pole or module. And for this device itself, actually, of course, in the real calculation, we have to include the development cost or others costs. But for the device itself, actually, for each, it costs about $100 US. So for one system with the wind compensation method, we need like 5 devices. It means for one system for about 40 by 40 meter, it costs about $500 US. It's still, I think, cheaper than 15,000 for the RTK GPS. And of course, the cost will be increased with the scaling up issue, because if we scale up the system, maybe for taking like 80 by 40, it takes twice. So like about $1,000 US. So that's why I discussed what is actually the scale of the area that make our system still give some benefit compared to the GPS.
So probably in greenhouse or some systems in the structure might be
yes.
suitable.
Yes, I think so, because also not only about this scale, the area issue, but also about our limitation. For current situation, our system actually can only give a good accuracy for 2 dimensions. So I think for the greenhouse with a relatively flat area, I think it's better, I think.
Anyone?
Just one suggestion. Could you show me slide 27, please?
27. Hi.
Here you give all with Doppler shift. It would also be good to see with no Doppler shift. If with no Doppler shift you still get a perfect circle, then there's no
yes.
change. But in order to show that there has been a change from no compensation to compensation, showing one with no compensation would help.
Oh, I think this is interesting, but how to say? Because likely we want to see that our system is effective enough, but to compare, I think this is possible to show the result with compensation when actually this result also clearly illustrated in this figure actually. So I think this figure can give a clear comparison between non-compensated and compensated system. So I think for the next, I think this is not necessary to, so this is non-compensated and this is compensated. From this result, I think this is enough to give a clear comparison that our system outperform this is non-compensated result.
Okay. I think much better than previous. Okay, I wish you can do defense very well coming Friday. So most of us join that and cheer him. Okay, thank you very much.
Thank you.